In episode 69, titled Designing the First Model, Baselines, Assumptions, and Quick Wins, the focus is on starting modeling with baselines to avoid false confidence, because the fastest way to mislead yourself is to build something complex before you know what better even means. Baselines keep you honest by setting a clear reference point, and the exam cares because scenario questions often hide the key decision in whether you can choose a sensible starting comparator and evaluate it correctly. In real systems, baselines also protect teams from spending weeks optimizing a model that does not outperform a simple rule already used in operations. The goal is not to worship simplicity. It is to earn complexity with evidence, using baselines as the measuring stick. If you begin with a baseline, every subsequent improvement has a clear meaning, and you can communicate progress without hype. Baselines are where you build trust with both the data and the people who will use the results. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A baseline is the simplest acceptable approach you can compare against, chosen to represent what you could do with minimal information and minimal modeling assumptions. It should be simple enough that it is easy to implement, interpret, and reproduce, yet reasonable enough that beating it proves real value rather than trivial improvement over nonsense. A baseline is not always random or do nothing, because those are sometimes too weak to be informative, especially when outcomes are imbalanced or when there is a strong seasonal rhythm. The exam expects you to treat baselines as meaningful references, not as straw men, because the baseline determines whether later performance claims are credible. In practical terms, a baseline answers the question, if we had to make a decision with minimal sophistication, what would we do? When you define baseline this way, you also clarify why it matters. It anchors learning and prevents overclaiming. Choosing the right baseline depends on the problem type, because different tasks have different natural simplest predictors. For regression, predicting the mean of the target is a common baseline, and in skewed targets, the median can be a stronger baseline because it reflects typical behavior more robustly. For classification, predicting the majority class is a common baseline, but you should recognize that in highly imbalanced settings, majority class accuracy can look deceptively high while being operationally useless. For ranking and prioritization, a baseline can be a simple score based on one clear risk factor or a historical rate, because ranking tasks are about ordering rather than about absolute probability estimates. For forecasting, a baseline often uses the last observed value or a seasonal naive approach that repeats the value from the same time in the previous cycle, because time structure must be respected. The exam frequently tests whether you pick a baseline aligned to the task rather than applying a generic rule, and getting this right shows you understand the objective rather than just the tools. You should set the evaluation plan first, because without a plan, the baseline and any subsequent model comparisons can be misleading. The plan includes split strategy, metrics, and constraints, which together define what good means and what evidence counts. Split strategy should match reality, meaning time-aware splits for time-ordered data, group-aware splits when entities repeat, and leakage-resistant splits when near duplicates or shared identifiers exist. Metrics should match the decision, such as error magnitude for regression, precision and recall for imbalanced classification, ranking metrics for prioritization, and calibration checks when probabilities drive thresholds. Constraints include latency, interpretability, fairness requirements, and operational capacity, because a model that is slightly more accurate but operationally unusable is not a win. The exam often embeds constraints in scenario wording, and the correct answer respects those constraints in evaluation design. When you establish evaluation first, you prevent the common trap of choosing metrics and splits that make your preferred model look good without reflecting real use. Before you build anything, you should check assumptions, data quality, leakage risk, and feature types, because these are the issues that make early results meaningless if ignored. Data quality checks catch missingness patterns, duplicates, and inconsistent units that can distort both baseline and model performance. Leakage checks ensure that features are available at the decision point and are not derived from post-outcome processes, because leakage can create dramatic but fake improvements over baseline. Feature type checks ensure categorical, ordinal, continuous, discrete, and binary fields are represented appropriately, because encoding errors can create false distance and false learning. The exam expects you to treat these checks as prerequisites, not as optional refinements, because a baseline built on leaky or misencoded data becomes a misleading anchor. Assumption checks also include understanding whether the target is stable and whether the data generating process is drifting, because those factors affect what performance you can expect. When you narrate these checks, you are describing how to make sure the baseline is honest, which is essential for everything that follows. The initial feature set should be quick and minimal, with only the transformations and encodings needed to make the data usable, because the goal is to establish a working reference, not to optimize. Minimal transformations might include correcting obvious unit inconsistencies, applying a simple log transform to a heavy-tailed variable when justified, and scaling features only when the chosen baseline model family depends on it. Simple encodings might include one-hot encoding for nominal categorical variables and ordinal encoding for ordered variables, while avoiding high cardinality expansion that can create sparse noise in the first pass. The exam often tests whether you can resist the urge to do everything at once, because a baseline iteration is about learning quickly and reliably. This approach also makes debugging easier, because if performance is strange, fewer moving parts exist to obscure the cause. When you build a minimal feature set, you create a clean starting line that makes later improvements attributable and defensible. A baseline should also be compared to naive heuristics used by the business today, because operational reality often includes informal rules that function as the current decision model. A business may already be using a threshold, a checklist, or a simple risk rule, and if your baseline cannot beat that heuristic, the model is not yet adding value. This comparison is important because it aligns analytics with actual decision-making, not just with theoretical metrics, and it helps stakeholders trust the evaluation. The exam expects you to recognize that baseline can include existing practice, not just statistical defaults, because the true baseline in applied work is what people already do. Comparing against business heuristics can also reveal that the heuristic is quite strong, which sets realistic expectations for improvement and guides where modeling efforts should focus. When you include this step, you show you understand deployment context and value, not just modeling technique. Skipping the baseline is a common mistake, and the exam often punishes it, because without a baseline, you cannot prove improvement. You can only claim performance. If you build a model and report a metric, that metric has no meaning unless you know what a simple approach would achieve under the same evaluation design. Without a baseline, teams can celebrate a model that is actually worse than a naive approach or worse than an existing heuristic, and they can misallocate effort toward tuning rather than toward improving signal. Baselines also guard against overfitting because they provide a sanity check. If a complex model barely beats a baseline, it suggests limited signal or weak features, while a large improvement suggests that meaningful structure exists.
The exam expects you to treat baselines as non-negotiable because they are the foundation of evidence-based iteration. When you refuse to skip baselines, you are committing to honest measurement rather than optimistic storytelling.
Scenario selection practice helps because baselines differ across churn, fraud, forecasting, and ranking, and the exam often cycles through these contexts. For churn, a baseline might be predicting the overall churn rate or using a simple recency measure, because churn is often driven by recent engagement. For fraud, a baseline might be a rule-based threshold on a high-signal proxy or a historical rate by merchant or device class, because fraud is imbalanced and ranking is often more relevant than raw classification. For forecasting, a baseline might be a seasonal naive approach that repeats last week's pattern, because seasonality is often strong and must be respected. For ranking, a baseline might be sorting by a single risk factor like prior incidents or recent anomalies, because ranking tasks often begin with simple prioritization heuristics. The exam expects you to choose baselines that respect the task's structure and constraints, not to apply a single baseline recipe everywhere. When you can describe baselines across these scenarios, you demonstrate flexible competence rather than memorization. Baseline errors are informative, and interpreting them guides feature engineering next steps, which is why baselines are not just a hurdle but a diagnostic tool. If the baseline performs poorly across all metrics and segments, it suggests the task is hard, the signal is weak, or the evaluation setup may be flawed. If the baseline performs well overall but fails in certain segments, it suggests that segmentation or interaction features may unlock improvement where it matters. If the baseline performs well in stable periods but fails during seasonal peaks, it suggests the need for calendar features or time-aware modeling. If the baseline is well calibrated but poorly ranked, it suggests features may help ordering, while if it ranks well but is poorly calibrated, it suggests calibration techniques or target definition adjustments. The exam often tests whether you can use error patterns to choose next steps rather than guessing, and baselines provide the cleanest error patterns to learn from. When you narrate baseline error interpretation, you show that you treat modeling as iterative hypothesis testing. Documenting baseline results is essential because it anchors iteration and stakeholder trust, creating a permanent reference for what you started with and why subsequent changes count as progress. Documentation should include the baseline definition, the evaluation design, the metrics achieved, the data time period used, and any pre-processing steps that were applied. It should also include known limitations, such as label noise or coverage gaps, because those constraints affect how much improvement is realistic. The exam treats this as governance and reproducibility, because without documentation, improvement can become a moving target, and teams can cherry-pick comparisons that flatter the latest model. Baseline documentation also helps future maintenance, because when drift occurs, you can compare current performance not only to the last model, but also to the original baseline to understand how far the system has moved. When you document baselines, you make evidence durable rather than ephemeral. Communicating baseline results requires careful framing, because the baseline is a starting point, not a final performance promise, and stakeholders may misinterpret early numbers as commitments. A baseline is meant to establish a reference and reveal the shape of the problem, not to define what the final model will achieve. Communication should emphasize that baselines are intentionally simple, that they establish a floor, and that the next step is hypothesis-driven iteration guided by observed error patterns. The exam expects this humility because it reflects mature analytic practice. You do not overpromise from early prototypes, and you do not hide limitations behind complexity. Clear communication also prevents a common failure where leaders see a baseline metric and either dismiss the effort as weak or assume future models will necessarily be dramatically better. When you explain baselines as evidence anchors, you set expectations that improvement must be proven, not assumed. A useful anchor memory is baseline first, then iterate with evidence. Baseline first means you establish a simple comparator under a defensible evaluation plan, and you do it before you invest in complexity. Iterate with evidence means each change is justified by a hypothesis, validated on held-out data, and compared back to baseline so progress is measurable. This anchor helps on the exam because it guides you toward the disciplined workflow the questions are testing, especially when distractors tempt you to jump straight to advanced algorithms. It also helps in practice because it protects teams from wandering into endless tuning without clear improvement benchmarks. When you keep the anchor in mind, you treat modeling as a controlled experiment rather than a creative project.
To conclude episode 69, name your baseline and then state one improvement hypothesis, because this shows you can start correctly and then plan an evidence-based next step. Suppose the task is churn prediction, and the baseline is predicting the overall churn rate for all customers, combined with a simple recency heuristic that flags customers with no activity in a recent window as higher risk.
This baseline is appropriate because it is simple, easy to explain, and directly comparable under a time-aware evaluation plan that respects customer timelines.
An improvement hypothesis is that adding normalized engagement rate features, such as sessions per week and change in engagement relative to a prior period, will improve ranking and calibration beyond the baseline by capturing early decline patterns. You would test that hypothesis by adding only those features, keeping the evaluation design fixed, and comparing results back to the documented baseline. This is the disciplined pattern the exam wants. Define a meaningful baseline, anchor evaluation, and propose a targeted improvement that you can validate rather than assuming complexity will automatically win.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.